Good afternoon again, everyone, and welcome to today's seminar in the College of Humanities, Arts, and Social Sciences Post-doctoral Fellow Seminar Series at Nanyang Technological University. My name is Joseph Scalise. I'm a postdoctoral researcher here at NTU, studying the history of Southeast Asia. The series that you are joining is part of an ongoing set of lectures on a range of topics in the humanities and social sciences. We have a talk coming up which promises to be exciting, and I would encourage you to register to attend, a repertoire of Dongba pictographs. That should be in 2 weeks' time, and emails will be sent out announcing it so that you can register in advance. Our talk today is entitled Pre-Modern Tropical Urbanism, Engineered Landscapes, and Resilience, the case of Angkor's water management system. Our speaker is David Brotherson. David has a PhD in archaeology with the University of Sydney and is currently a postdoctoral research fellow with the School of Humanities at Nanyang Technological University. His research interests include the demise and transformation of Angkor, pre-modern urbanism, trade and exchange, and socio-ecological dynamics. I'm certain that for many of us, an intellectual exploration of archaeology in Angkor is a welcome respite from the craziness of the news cycle today. And I, for one, have been very excited about this topic. So please join me in welcoming David Brotherson, our speaker today.
Thanks, Joseph. Good afternoon, everybody, or good evening, good morning, wherever you are. Thank you for joining us. Let's get underway. As you see from the panel here, if you have questions, you can enter them into the chat panel and we can address them at the end of the talk, which today I'll be going through my PhD research, which focused on the demise and transformation of Angkor and how Cambodian urbanism transitioned into the early modern period. We'll consider these results and implications of my research within the framework of socio-ecological systems. So, in brief, Angkor has long been renowned for its massive temple complex, but in recent years, it has been identified as the most extensive pre-industrial settlement in the world. By the late 12th century, most of its estimated 750,000 inhabitants lived in a vast, low-density, dispersed agrarian urban settlement that sprawled over more than 1,000 square kilometres beyond that central temple complex area. This system was given functional coherence by a network of infrastructure. Now, popular literature usually frames Angkor's demise as one of catastrophic loss due to an invading army, but this narrative is based on less than reliable textual sources. In contrast, material culture indicates this period was one of change and transformation. That said, Angkor clearly experienced a drastic drop in population in which various interacting factors operating at different scales of time and space played a part. These factors include unsustainable subsistence practices, an over-reliance on engineered infrastructure, unprecedented climate variability, and the emergence of new economic opportunities elsewhere. And before we dive in, we're just going to define a few things to give you an idea of the scope of the study. By pre-modern, we mean pre-1450 or thereabouts, and after that is the early modern period, which is 1450 to 1800 or so. Of the tropics, we're looking specifically at the dry zone of the monsoon region, and urbanism. Urban tends to have a variety of meanings whenever it is applied around the world, but for my purposes, I like the definition that refers to intensely developed environments designed, built, and inhabited by people. So that idea shares a lot of common ground with an engineered landscape, which is essentially a human-modified environment. And by resilience, we mean the ability of a system to prepare for threats, absorb impacts, recover and adapt following persistent stress or a disruptive event. Now, I mentioned in the abstract that we'll be looking at a socio-ecological system. Now, this is defined by Johnson et al. As a particular group of people, a particular set of resources, and a particular set of institutions or mechanisms that operate together. Over time, human behaviour and institutions evolve and adapt within a set of prevailing conditions and expected disturbances or stresses. Now, one might tend to focus on natural variability when thinking of disturbances, fire, flood, hurricanes, etc. Climate variability, whether that's seasonal or annual variation. But we can also broaden the scope to incorporate a wider range of mechanisms that deal with social or structural variations. So laws that deal with taxation, commerce, or property ownership, or centralized control. And the most significant mechanism for our study today is infrastructure. By analysing how these systems have operated in the past, we can have a long-term perspective and a more thorough understanding of the potential solutions available to us today in how we manage our cities and their environments. Now, the environment plays a significant role in the way we live our lives, what we eat, how we dress, the types of houses we inhabit, the time of day we recreate. Yet while it unarguably is an influential factor on our behaviour, it is not deterministic, because human ingenuity can devise structural mechanisms and institutional strategies to make these places more accommodating. Thus, so to contextualise the functional case for Angkor's water management infrastructure, we first need to consider its environmental setting. So Cambodia is characterised by a vast central floodplain extending from two main water features, the Mekong River in the east and the Tonle Sap Lake in the west. Mountain ranges are located on all sides, more or less, of the country. These create a rain shadow that results in a pronounced dry season each year. Angkor is situated in the northwest of the country on a low relief floodplain that descends gently from northeast to southwest. That's from the Kulen Hills to the lake's edge. Angkor and modern Khmer settlements were all situated in these low-lying areas, typically between 10 and 30 metres above. Now, the Tonle Sap, the Great Lake, experiences a remarkable flood pulse phenomenon during the wet season each year, which sees the water level rise up to 8 metres and its total area quadruple. This is due to the flat landscape of the country, coupled with the surging flow of the Mekong, which results in its waters backing up and backflowing into that of the Tonle Sap. So the Tonle Sap River reverses direction. An important ecosystem has evolved within this environment as numerous fish species breed in this flooded forest around the lake's edge. The Tonle Sap is one of the most productive bodies of freshwater fish in the world. It has been Cambodia's primary source of protein for millennia and remains so today. And that vast floodplain around the lake is also ideal for growing rice. We've mentioned seasonality. Well, Siem Reap's climate is sharply seasonal, with a dry zone climate which presents challenges for permanent settlement, alternating between an abundance or an undersupply of water. While approximately 1,200 mils falls each year, the wet season accounts for 88% of that, and during the dry season it only rains about 15 days on average. There is one aspect of the natural environment which works to mediate that discrepancy, and that is the Kulen Hills. As a porous sandstone plateau and source of the rivers that flow through the city, this aquifer absorbs part of the runoff and releases it more gradually throughout the year. The Kulen also experiences significantly more rain, about 1,800 mils. There is also a significant amount of annual variability that we can see in these charts. Now, the dry season is evident, the rhythm of the dry season is, but the total precipitation and its tempo of delivery changes quite a lot. Climate scientists suggest this occurs due to the complex climate dynamics, based on the interaction of three major regional weather systems. That's the Indian, the East Asian, and the West-North Pacific summer monsoons. And we see that mainland Southeast Asia is sandwiched in between all three of them. So the annual variability in rainfall is a significant risk factor for wet rice agriculture. Rice is a water-intensive crop, and rainfall is by far the single most important non-anthropogenic determinant of yields. The best yields occur when the rains arrive and endure as expected by the farmers. And this just shows what 2015 was a dry year, the Struss Strong, which is in our opening slide, bone dry that year. So there's a lot of variation. But a more immediate concern than one's seasonal food production strategy are our daily needs for water. Thus, it comes as little surprise that prior to the development of water storage systems, most settlements in the prehistoric period were very close to natural water sources, either along the banks of the lake or the rivers. Now, by raising a leveled earthwork, what we call an occupation mound or a house mound, in these locations, the Khmers of prehistory could situate their homes on dry ground, clear of the monsoon floodwaters, but also surround them with rice fields that were sown in rich alluvial soils of a floodplain. Over time, as bronze and later iron technology was harnessed, the ability to work the land more effectively led to more efficient farming techniques, higher crop yields, population expansion, and growth in the number and size of settlements. Now, the earliest forms of water management came in the form of concentric moats and embankments which encircle the occupation mounds during the early centuries AD of the late prehistoric period. Building infrastructure to store water, it avoids the uncertainty of unpredictable rain or drought. Storing water brings a measure of security, and it becomes a resource that can then be controlled. Pomlavia is one such moated site in Siem Reap. Which is, let me just mute my thing. There we go. It's located near northwest of Angkor, where it would later be established. Angkor, that is. Now, various other functions have been suggested for these moats, including defense, aquaculture, or conspicuous display. Yet, the topography provided by LiDAR shows that Lavia's outer embankment has a consistent height of 13 meters above sea level around its entire length. See, the landscape is sloping, descending from northeast to southwest, but that embankment maintains the same height. A consistent absolute height for the top of the embankment suggests it was designed for water storage. Okay. Now, Lavia is contemporary with similar moated sites in Thailand. The appearance of these impressive earthworks coincides with an increase of social differentiation in the mortuary record. Construction of earthworks is no mean feat. It requires considerable manpower, and one interpretation is that the organisation and control it necessitated can be attributed to the development of social hierarchy. Now, we argue that if a large or increasing population was to be sustainable, some form of water management was required. Now, we've already observed variability of rainfall in recent years, but paleoclimate studies give us a long-term perspective and indicate variability throughout the past. These are based on natural archives, such as cave deposits and tree growth rings. Two large-scale phenomena that are correlated with Angkor's rise and demise are the medieval warm phase, which is roughly the 9th to the 12th century, and the transition into the Little Ice Age. The Little Ice Age, 16th to 19th, but that transition is the 13th to 15th. So in general, the warmer conditions of the warm phase in the Northern Hemisphere, brought with it more precipitation across Southeast Asia. Not just more rain, but a more even annual distribution, with a longer wet season and fewer deluges that can damage crops or irrigation works. As Lieberman and Buckley argue, these conditions make the rain more usable and provide the ideal setting for political and agricultural expansion, especially in the dry zone region of Angkor. As Angkor grew, its water storage capacity would achieve staggering proportions. Now, in contrast, the transition from the warm phase to the Little Ice Age saw significant instability in monsoon strength with frequent and high amplitude oscillations between wet and dry conditions, we see here. It also contains some of the driest conditions in the record, a prolonged drought in the first half of the 13th, to multi-decade droughts in the late 14th, early 15th centuries, and which bracketed some very intense monsoons as well. So these charts are based on regional proxies from South Vietnam and other sources, but cave deposits from Cambodia itself exhibit a clear growth hiatus, is best explained by prolonged drought conditions during the 14th to 16th centuries. Now, bearing in mind that even a 10% reduction in rainfall can trigger a drought, during this period, rainfall was reduced by between 20 to 30% for periods of up to 30 or 40 years. So we argue that these minimal rainfall conditions stressed the food production capacity of Angkor and would prompt alterations to its water network that made it less resilient to climate variability. So as for our network and its role, we note that water plays a significant role in the religious practices of Cambodia today, and it was likely equally important in the past. The worship of Shiva was the dominant royal cult for hundreds of years. The form of the linga and yoni strongly suggests that ablutions were part of those royal rituals, as envisaged here by Maurice Fierve for the April 1960 issue of National Geographic. And atop the Phnom Kulen, the headwaters of the Siem Reap River, is the site of Kabal Spian, which features numerous carvings evoking the power of the god and Vishnu. The massive barai, these are reservoirs defined by earthen embankments, were also sacred. The four at Angkor each feature a Mabon, that's an island temple, at their centres. This is the West Mabon, or the West Barai, and this was where the giant, the colossal fragment of Vishnu Anantasayan was recovered in the 1930s. So it seems the power and legitimacy of the king was also tied up with water. As Georges Sedez wrote, "The good king is one whose rule is accompanied by regular seasons and good rain, with catastrophe being the consequence of any error in ritual." So in addition to its ritual function, French archaeologist Bernard Philippe Grolier saw the barai as structures which impacted substantially on the residential and agricultural landscape of Angkor. Well, yes, they constitute, many square kilometres of space that they take up. He theorised that Angkor was a hydraulic city, that is, an array of suburbs given coherence by a large-scale network of infrastructure designed principally for rice irrigation. In some of his estimates, Grolier envisaged vast areas of land irrigated and even suggested multi-cropping could be achieved to support a population well in excess of 1 million people. I mean, this was an upper estimate. He did have more conservative ones as well. Grolier also noticed that the failure of this system caused the collapse of Angkor and Angkorean civilization. Now, in contrast, some other scholars have argued against seeing the barai in functional terms and make the case for theocratic hydraulics, that they were components of a sacred geography arranged around according to Hindu and Buddhist precepts. However, one of the main pillars of this position was the claim that the barai had no inlets or outlets which an irrigation system would need. But this claim was only possible then due to insufficient fieldwork. At the time, these features had not yet been identified. Now, Grolier had understood the need for a comprehensive archaeological map of the areas beyond the monuments to properly assess his theory, but he was unable to achieve this because of the Civil War and the Khmer Rouge period. But once peace returned to Cambodia, this work could resume. Inlets and outlets have since been identified, initially by Christophe Potier, and then later in collaboration with the University of Sydney's Greater Angkor Project, GAP, through a combination of analysing aerial photos, ground penetrating radar, targeted excavation, and most recently, LiDAR. But irrespective of the network builder's intent, these components were capable of influencing the flow of surface water, which they still do today. So we argue that the Barai most likely served numerous functions, both symbolic and pragmatic. So, as I said, inlets have been located on all 4 Barai. They are normally situated at the northeast corner. This is the high point. This is where you could get maximum amount of water stored if you're filling it from the northeast corner. Now, one type of outlet was the spillway, which would be located in the middle of the east bank, such as Krolramia on the East Barai. This was a permanent mason. In contrast, there is evidence that a temporary breach in the earthworks was also used to discharge water, as the infrastructure we see here at the southwest corner of the West Barai suggests. Note the numerous notches that we see along the south bank. The embankment is thinner in these places and thus easier to breach. Note also the rectangular grid that aligns with the notches, is associated with them and is alignment with them, and the depressions, the canals, which run off to the southwest and southeast. Now, significantly, the arrangement of rice fields between these 2 channels is arranged in a fan shape. That is, the field's morphology is closely related to and generated by the channels from that West Barai grid. So here we have a spatial and functional relationship that extends from the Barai bank to the collection grid, to these channels, and finally to the rice fields themselves. Amongst these rice fields, not just at the fan, but around the entire dispersed settlement, are hundreds of these temple communities. They consist of a small village shrine in red, associated with house mounds and ponds that are in brown and blue. Given the possibility of weak monsoons, even if the Barai was simply used to ensure an adequate supply of water for one annual crop in just some parts of the system, they would have added a significant measure of resilience to the operation of agriculture. Now, if we consider the network as a whole, it consists of features for water storage and water movement. There are 2 types of storage devices. There are those that are excavated into the ground. They store water below the surface in a ditch or a depression. And there are those that retain water above the surface level. That water is held in by giant earthworks. Temple, moats, and household ponds fall into the former category. The Barai are in the latter. Now, water movement was achieved with excavated channels or raised embankments. Canals can shunt water around the landscape, but could also be used for transport, especially for bulkier cargoes. 3 types of canal. They are delivery, dispersal, or disposal. A delivery channel connects the natural watercourse to the Barai inlet at the northeast corner. So you see this one zigzagging here. Dispersal and disposal channels, however, are associated with the outlets. Dispersal channels run from northwest to southeast, and disposal channels run from northeast to southwest. They connect the outlet of the Barai to the lake by the shortest path. Now, the primary distinction between dispersal and disposal channels and their function are their relationship to the gradient. By running across the gradient, a dispersal channel could distribute water to areas far removed from its natural source. This is maintaining a relatively constant elevation as it does so. It therefore had the potential to irrigate land all along its downslope side, down here, by breaching that bank. In contrast, the disposal channel, which runs with the gradient, was ideally positioned to dispose of excess water into the lake. These canals also provided means for rivercraft to access the city. Okay. The delivery channels also notably take a zigzag course across the gradient, which forces the water into a longer and therefore slower route across the landscape. Also, each of these right angle bends in there would substantially reduce the flow rate as well. So these characteristics reduced the risk of erosion damage to the system. The Barai themselves could hold millions of cubic meters of water. So notwithstanding their potential for irrigation, they could simply have stored water for use in the dry season. They had potential to siphon off excessive flows to prevent flood or erosion damage during freak inundations in the wet. And by retaining a body of water above the ground surface, just by seepage, that would effectively raise the water table in all those areas, the living spaces around. So this would help ensure that all those little household ponds, which were rain-fed but otherwise reliant on groundwater, they could be of use in the dry season. Now, as I said, Angkor's Barai achieved staggering proportions. The West Barai in the early 11th century is 8 kilometers long, 2 kilometers wide. It's defined by a bank that's 10 meters high and 120 meters wide at its base. These were built successively between the late 9th and the late 12th century. Over time, the general trend is they're installed further to the north, that is further from the lake's edge, as were the foundation of temples contemporary with them. As more Barai were built, so too were more state-level monuments that centralized control of resources into the hands of fewer elites. Now, as mentioned, storing water turns it into a resource which can be controlled. And social institutions that regulate its use are key components of water management systems. Two types of control systems are envisaged. Top-down systems, which imply hierarchy, centralization, and state control, and bottom-up systems, which imply heterarchy, localization, and community control. Now, Klassen and Evans have analysed the diachronic relationship between the installation of new temple communities and hydraulic infrastructure. They argue that initially, the installation of new communities clusters around epicenters and state-sponsored hydraulics, suggesting the presence of a hybrid system of both top-down and bottom-up management. Yet after the 11th century, the trend is towards construction of state-sponsored temples on lands that were previously owned and developed by these temple communities. So this is like a process of centralization through the concentration of land ownership and indicative of a dominant top-down management approach. So the climax of these developments was, of course, the reign of Jayavarman VII, who took the throne in the late 12th century. He's perhaps the most revered of Cambodia's kings, and his legacy in terms of religious monuments and urban development is hard to overstate. Its centerpiece was Angkor Thom, the Great Walled Citadel, walling in the urban center. The great temples of Bayon, Prakan, Taprom, Bante Kadai, the Jayatataka, Barai, Nakpuan, Tasom, and numerous other smaller monuments all date to his reign. Inscriptions he installed recalled the thousands of people that staffed his temples and even more villages that supported them with a rice tax. For example, the Ta Prom inscription states it had 18 high priests, 2,700 officials, 2,200 assistants, 615 dancers, along with many monks, commoners, and temple servants. The rice production of 3,000 villages was the property of that temple. So operating these complexes was clearly a significant burden on the surplus of the state. The engineered landscape in and around Angkor Thom is structured very differently to the temple communities we saw in the periphery. Here we have a formally planned orthogonal grid that's orientated to the cardinal directions. We suggest that most of the people living in this area were officials, administrators, merchants, or staff of the temples. One thing is clear from Angkor Thom's topography. This area was not used for rice production, but rather contained a higher density of urbanized occupation. This segment of the population, numbering in the tens of thousands, were thus reliant on the crop surplus of the surrounding agrarian urban food producing areas, if not further afield. Now, in terms of hydrology, the placement of the Jayatataka and its outlet near the southwest corner suggests it served as the holding tank for Angkor Thom's delivery system. This was Angkor Thom's Barai. However, a conundrum exists because eventually the Jayataka was disconnected from its delivery channel. At no point does the course of today's Siem Reap River enter into a Barai. Within the long-term perspective of Angkorian water management practices, this configuration is an aberration and stands out in stark contrast. Why disconnect the Barai and do away with its various benefits? We argue that an acute water shortage was the likeliest scenario. If the water flow is weak, it would not be able to sufficiently fill the Barai to be of use. And once it's spread too thin in that great surface there, it might just soak into the surface or evaporate off before it has time to accumulate. So from a functionalist perspective, this modification to the network equilibrates the operation to an extended period of drought. As I will argue, bypassing the Barai was just one of several changes made to this configuration, which all relate to the persistent droughts of the warm phase to Little Ice Age transition in the 13th and 14th centuries. The elements crucial to our discussion today are in this area and relate to water delivery to Angkor Thom. So, okay, this is a provisional model that only further research and more excavation will be required to confirm. However, excavations by GAP have revealed the relative chronology between various features, and LiDAR reveals topographic and spatial relationships, which we synthesize in our model. Now, the first stage is the construction of the Jayataka and its initial outlet, which we've shown here. From this outlet, a depression heads due south. That would have been a disposal channel, but we argue it would also have been divided here, it seems, to deliver water in a westward running channel to the northeast corner of Angkor Thom. Next is the North Bank Wall, this giant earthwork with a 8-meter high masonry wall that retains it on the north side. Now, this wall postdates the moat of Angkor Thom. It's built over at the west end. This embankment and wall is built on top of this bank on the outside edge of the moat. It also runs through that Jayataka outlet channel. So we've got a feature which postdates the late 12th century here. We also argue that at this time, the North Bank Wall is contemporary with the bypassing of the Jayataka. So instead of going into the Barai, the water's being sent around its east end and then into this corridor between the Barais and westward like so. This would also be when this feature, the dam bridge, was installed. It's an earthwork, but it has two laterite culverts. This, in this arrangement, because we don't have the holding stage mechanism of the Barai, the dam bridge's culverts function as a stepping down mechanism to slow the flow of that water going through it. Significantly, the north culvert, through which the river flows today, is in a ruinous state. The next up is the construction of this mound, which I affectionately call the mound. On top of it is a stone pavement and the remains of a platform base. Now, section profiles that run across the North Bank Wall, color-coded them here. They show a consistent profile on the north face, which is defined by that retaining wall, but on the south side, we have those profiles vary somewhat. And the profile which crosses the mound and the wall indicates the North Bank Wall is less substantial at this point, the blue line. So we interpret this as evidence that the mound was built after the wall and has even used a bit of its soil in the construction process. The other relationship here that I argue is the spatial association between the mound and this cutting through that embankment. Now, They're immediately adjacent to each other. A general observation of Angkorian earthworks is that each raised feature is associated with an adjacent depression. Embankments are flanked by ditches. Ponds have raised banks around them. The embankment around Angkor Thom is enclosed by its moat. The North Bank wall has its moat on the north side. Okay. At its simplest, if you need to dig a hole in one place, you would pile up the spoil heap next to it. Now, what I propose is that the proximity of the mound to the river cutting makes it the most likely destination for the spoil heap from this cutting. Now, we'll probably never know for sure, but if this theory is correct, it would fall within a very consistent pattern of earthwork construction at Angkor. So this cutting divides the flow of that channel that was coming through the corridor, divides it in two. We're still sending some west, but they've decided to send part of it south. So the mound was excavated by the Greater Angkor project to characterize its substructure and assess the date of its construction. Artifacts and organics obtained from within the mound, our charcoal charcoal pieces, their provenances, their determinations. This is the plot. All the artifacts within the mound are from the 13th century or earlier. But we also have an iron artifact, this crampon, that was found on top of the mound in the stone platform. Now, crampon is like a metal staple that would run between two adjacent blocks and sort of hold them together. This crampon was analysed courtesy of the Angkor project, directed by Stéphanie Leroy of the Centre National de la Recherche Scientifique in Paris, to radiocarbon date its time of smelting. The basic idea for this is that iron alloys contain carbon, tiny amounts, in the steely zones of the metal, which originated from the charcoal used to smelt the iron ore. These trace amounts can be extracted, its isotopic ratio can be determined, and that can give us a radiocarbon date. Now, our crampon is the uppermost date here. It dates primarily to the latter part of the 13th century, and it provides a terminus antequem for the mound's construction. The mound cannot be later than the crampon. So if the Barai was first bypassed due to a water shortage, why then would they divide that single channel's flow in two? We argue that it was another indication of a critically weak supply to distribute what little water there was as far as it could go. And instead of putting it in an open field of the Barai, they're still keeping it in narrow channels, so it's got less opportunity to evaporate. All right. If that were the case, the channel division would be the most direct way to deliver water to the area east of Angkor Thom, which had roughly half the population of those that were living inside Angkor Thom itself. So we envisage a scenario in which the water table was depleted, such that household ponds were dry. That's what all the little pockmarks are, household ponds. And perhaps the only way thousands of urbanites in the central area could access water was via these small channels. Now, alternatively, it is conceivable that the flow division was enacted to dispose of excess water. You know, we are just sending it south into the lake. However, if there was in fact an oversupply of water, they did not have to dispose of it. Like before, they could just store it in the Barai and reconnect it by, reconnecting either the Jayapataka or the East Barai to the system. But they didn't. So we return to our hydroclimate reconstruction and consider the periods of drought around this time. If the mound's construction is indeed associated with the channel division, that would imply it's happened by the late 13th century, and it's probably the first half of the 13th century drought which prompted it. However, if the mound and cutting are not contemporary, then it's conceivable the division took place during the mid-14th century drought. And then again, If these substantive changes to the water management network were unrelated to the availability of water, then, who knows, right? However, I feel a functional explanation for these modifications makes a compelling case. In any event, these modifications were substantial and deliberate acts. Remember that retaining wall was an 8-meter high construction, and they had to carve a channel through that embankment. So these were unlikely to have been done haphazardly. That said, there is a terminus antiquam for this final configuration of the network. It had to have happened. It had to be in that configuration when it was subject to the extensive erosion damage, which we can date to the 14th or the early 15th century. These are the determinations there. Excuse me. Now, excavations of the disposal channels to the south have found that they are filled, these south channels, with large deposits of coarse, cross-bedded sands, the result of large quantities of rapidly moving water that abruptly slowed as it reached the floodplain. The source of these sediments was the riverbed of the Siem Reap Channel itself. It is cut down by up to 8 meters along its course for tens of kilometers to the north. And you can see in the shade relief of the map here that is why it's so dark. It's 8 meters lower. Now, the organics contained in those sediments is where we get these dates from. They give a consistent range. And we note also that the water management network had sustained strong monsoons in the past, but argue that its 14th century configuration was overwhelmed because there was no mechanism to deal with excessive flows. The Barai had been disconnected. So how might this event have taken place? Well, Jacques Dumaset had noted the dam bridge is partly destroyed and envisioned a scenario in which its culverts were blocked by an accumulation of debris, like a logjam, while the corridor takes water between two Barai, the corridor is still delimited by those Barai embankments. So water could still accumulate on the outside of them, which is what the scenario envisages. Potentially millions of cubic meters of water held back by these culverts. Also, you can see the profile of this dam bridge. It's more slender. It's not as substantial as these other embankments, so that could have also been a problem. In any event, the erosion damage to the Siem Reap River and sand deposition downstream is consistent with the action of great surges of water. So whatever the specific manner in which the damage occurred, once it had, the hydrology of central Angkor was seemingly irreparably altered. The downcutting of the channel would lower the water table in the central area, leaving those ponds dry. It would prevent the movement of water across that central channel, severing the network in two. Restoring those facilities was either too difficult or not worth the cost of repair, and relocating seems to have been a simpler option. That said, sediment archives and residential debris from the central area indicate the daily activity of Angkor's population was already changing in the early 14th century. So this is based on a core from the Angkor Thom moat, which is analysed for organic charcoal and pollen types. It shows two distinct phenomena. First, the amount of soot, the organic charcoal, which is created from the annual burn-off of rice fields or daily cooking. That seems to diminish from the 1320s, which they are using it as a proxy for land use gets a negative value from the 1320s onwards. Secondly, in the 1370s, the dominant species of plants in the of pollen in that core changes from woody and shrubby types to aquatic plants and ferns. That is, by then the moat was covered by a mat of floating vegetation. The implication is that it had ceased being maintained. Such work requires a large labour force and some form of central organisation. This moat is 12 kilometres long, right? The author's conclusion was that the lack of organisation meant the elites were not present and had probably moved on, and the shift south to engage with new economic opportunities of the nascent age of commerce may have been their destination. But more significantly, In addition to the abrupt decade-scale collapse of the water network in the 1400s, the decrease in land use indicates that Angkor also endured a much longer century-scale demographic decline that started in the 1300s. Now, gap excavations reveal essential areas within temple enclosures were also disrupted in the 14th century. At Ta Prohm, Ta Prohm occupation ends during the 14th century. At Angkor Wat, there is a residual occupation that continues into the early modern period, but there's still a significant break in those radiocarbon dates in the 14th. We relate these phenomena to the various climatic, political, ideological, and economic upheavals that we associate with this time. So our proposed model for the breakdown of the network seems to have been a final coup de grace to an urban system that was enduring numerous other stresses in the late Angkorean period, specifically that of the higher density urbanized population of that central area. But for the final part of the talk, we're going to consider the occupation history of the peripheral area throughout Angkor's demise. And this is what I've been talking about. The central area, it's an arbitrary 5-kilometer radius circle defined by that dashed line, but it contains all that formally planned grid of the central urban area. The periphery is what's outside it, all right? So, occupation history of the peripheral area is when we now turn to ceramics. They're the most durable and commonplace form of material culture that was used by everyone, especially cooking pots and bowls. So they're a useful proxy for the presence of residential activity. The basic method to study such a large area, remember this is it's more than 1,000 square k's, is to collect surface scatters, what we find on the surface. With a suitably large collection of datable ceramics, we can look for patterns in artifact variability at different locations across time. So we couldn't survey everywhere, but we use these large transects. They're 5 kilometers wide, up to 30 kilometers long, and we visited every single house mound and earthwork in those zones. Throughout the Angkorean period, a thriving ceramics industry produced glazed and unglazed stonewares and earthenware cooking pots. However, all known production centres had ceased operations by the end of the 14th. So if we're to assess Greater Angkor's occupation history after the water management network breakdown, we can't rely on Khmer ceramics. But the solution is to focus on imported ceramics, what we call trade wares. The majority of those found at Angkor are overwhelmingly Chinese. But during the Angkorean period, trade wares usually only comprise a very small percentage of the ceramics found in a general occupation site, somewhere in the order of 1 to 2%. But the locations where they're found in greater numbers suggest they were high value and perhaps status markers, because excavations within Angkor Thom have found them in higher proportions, 5 to 10%, and within the Royal Palace, they significantly outnumber the local wares. They make up 2/3 of what they found there. So Dawn Rooney has suggested that within the royal establishment, Chinese ceramics were the preferred ornamentation and for serving food, right? So surveys similar to ours have revealed early modern period trade wares are also found in other parts of Cambodia. But our survey team collected ceramics from over 700 sites, and in total, we have 2,541 datable tradeware sherds to look at that patterning of artifact variability. Just quickly, the different types we find. Like I said, mostly Chinese. Got a lot of these beautiful shapes and glazes and decorations, whiteware, Qingbai, Celadon, etc. Longchuan, Jingdezhen, Dehua. We get also a considerable amount of early modern period Chinese. Now, this is the later stuff, post-17th century, tends to be a little more coarse in the way it's manufactured. It's mass-produced. Sometimes referred to as kitchenware. And then we also have non-Chinese. It's a very small percentage of what we found. Second most common is Japanese, but then there's maybe only 120 pieces. Thai and Vietnamese would be a dozen or so each. We get also, I've called this Thai, but it's Chinese stoneware, but it's made exclusively, or originally exclusively, for Thai aristocrats. This is Buncherong, the various dates that they relate to. So we collect, clean, sort, count, weigh our ceramics, and then we look at the broad patterns of their temporal characteristics. So for this chart, each sliver represents a single piece, and it extends from left to right across its date range that when we know it was being made or being used. And we see distinct characteristics in the temporal patterning. The vast majority are either Angkorian from the 11th to 14th, or in the 18th and 19th. And while they're in the 15th to 17th, there is a notable reduction. There's still some presence there. Now, if we consider the spatial patterning across time, we see interesting patterns as well. So from the Angkorian period into the 16th century, the post-Angkor early modern period, there's a great reduction in the number of ceramics and the number of sites, but they are still generally dispersed throughout those survey areas. There's less, but it's still scattered. And there is, the only place they're clustered is down here in the southeast. When we look at the later period, 18th century, again, there's a resurgence in the numbers, but they are still dispersed. And again, the only real clustering is in the southeast. This is near the lake's edge and in the proximity of the Rolua River. So several sites which appeared active during the early modern period were studied further with test pit excavations to characterize their occupation histories. Now, I'm going to show you the results of Kokkonchray, which is one of these little dots down here, which are typical of the distinctions in artifact densities we found throughout time. That is, the bulk of that deposit is from the Angkorian period. If we look at our trade wares here, we can see that even up within 50 or 40 centimeters of the surface, we've still got Angkorian period Chinese trade wares. So this is showing you the weight, the mass of the various types throughout the stratigraphy. In contrast, the early modern period materials, are found only in the uppermost layers, normally within that 40 centimeters of the surface. We also see that the rate of deposition has decreased significantly. So that was 500 years there, and this is probably 700 years of deposition. So it's a huge change in the rate of the amount of activity and the rate of deposition. The great heaps of debris generated in the Angkorian period is basically topped by a superficial smear of early modern period activity. Evidently, the people living here were doing so in such a low density configuration that they could function without those top-down water management structures of state-level infrastructure. The community-based systems of rain-fed rice fields and ponds and perhaps small-scale water control mechanisms sufficed. This subsistence mode, it predates the rise of Angkor, and it proved more resilient than the urbanized system in the central area. Finally, despite the abundance of post-17th century trade wares, they represent a different proportion of the assemblage and presumably a different type of activity to that of the Angkorian period. A rough calculation based on contemporary Khmer ceramics shows that the trade wares are no more than 7% of the total mass collected, and almost certainly considerably less. In contrast, the early modern period trade wares are the only ceramics we can date to that period with certainty. The 19th century French explorer Francis Garnier noted that the Cambodian markets were predominantly stocked with Chinese ceramics. Thus, what we have therefore likely represents the entire assemblage. So another observation is a value-based judgment. Like I said, the post-17th century ceramics were mass-produced on an industrial scale. They're less carefully decorated, etc. They were thus probably less expensive and more likely to be used on a daily basis. So if we follow Rooney's suggestion that Chinese ceramics were elite status markers in Angkorian times, by the 18th century, they have taken on a utilitarian function within Cambodian society. So now we're going to look briefly at the evidence for early modern period ritual activity and consider its spatial extent. These are the earlier UTM Buddhas, the Satchapranadin, the early modern period inscriptions of Buddhist pilgrims that were primarily at Angkor Wat, but also a few other locations. We also have the major temple reconfigurations, the colossal Buddha in Parinirvana at Bapuan, the Colossus Dhyana Mudra Buddha at Phnom Penh, and the reconfigurations to Bakan at Angkor Wat. And then we also have cremation burials, cremated remains stored in covered bowls that were buried at the bases of these old temples. They're at Kokpatri and Lalai. The takeaway from this is that most of this is happening in the central area, and it's mostly near the Siem Reap River. The cremation burials are outliers. So while the number of active shrines within the central area from the Angkorian period has been reduced from dozens of Angkorian period shrines to just a few early modern period sites, the remnants of the Siem Reap River, which is our blue line, suggest it was still being served as a means for pilgrims to access the old temples for ritual activity. So to compare the spatial patterning of activity in the central area and the periphery, we note the center contracts to form a linear arrangement along the course of the Siem Reap River. Residential activity in the periphery is reduced significantly, but it's still dispersed across the landscape, but the only notable clustering is near the Rolowas River. Thus, the river systems seem to constrain the extent of early modern period activity, a characteristic which correlates with Grollier's observations of early modern settlements down in the Phnom Penh area. Okay. What does this call to mind? That our early modern period pattern has striking parallels with the prehistoric period. And I think this is as simple as the case for water management gets. When it is operational, water management allows the settlement to extend 20 to 30 kilometers from the lake, but without it, the clustering really only appears along the rivers or next to the lake. So, given our survey transects didn't really sample much of the Puok River, that's the one over this side, or that disposal channel, it's possible that additional evidence of early modern period occupation might be found in that area. Be interesting to have a look there, close to the lake and along the Puok. So to conclude, oh, we've done well. Time. The socio-ecological system that saw Angkor rise to dominate mainland Southeast Asia for centuries was structured around its water management system. It provided rice production a measure of resilience in drier years and could prevent flooding and damage to infrastructure in wetter years. It made water more readily accessible to the people for their daily needs. In fact, I'd say it was so successful that it led to a social system that could arguably be called top-heavy, with too many in non-food producing roles, and they were too far removed from perennial water sources. Ultimately, this network seems to have been better attuned to the predominantly wetter conditions of the medieval warm phase. We argue that the uncertainty of the warm phase to Little Ice Age transition led to alterations in the network that would leave it critically exposed to environmental stresses. And once the damage was done, Angkor's role as it was at its apex, was untenable. However, the only element of this socio-ecological system to have failed was the extensive urban system of Angkor. The Khmer state relocated and endures, as does the monarchy, the elites, the religious establishment of the Sangha, the rice farming peasantry and their love of prahok. In fact, the most conspicuous change between Angkorean and early modern Cambodian urbanism was its scale. The vast low-density urban complexes like Greater Angkor would not reappear, but were replaced by relatively compact towns or linear arrangements along rivers. While some form of water management is associated with them, notably the prak along the flood banks of the Mekong, these were scattered along the river and never achieved the scale of Angkorean works. While the Barai enabled the people of Angkor to sprawl out tens of kilometres from the lake's edge, their descendants generally kept the lake and rivers within walking distance. So Victor Lieberman argues that the post-classic states of early modern Southeast Asia were more economically diverse with more robust institutions. So while painful droughts might still occur in that time, they were able to endure them more effectively than their classic period ancestors. That is, these early modern socio-ecological systems, were more versatile with more mechanisms available to withstand disturbances. Rice and fish remained Cambodia's staples, but the state was more actively engaged in trade and commerce, which formed alternative bases of power, wealth, and stability. So too, our own economies should be diverse and not over-reliant on any one market or resource, especially if it is finite. So finally, it appears that one of the primary benefits of low-density urbanism was food security, in that food production and consumption were closely associated. If anything, the global pandemic has highlighted the shortcomings of supply chains that are reliant on importing food and goods from afar. Now, while operating with vastly different transport and communication technology, the urbanized population of central Angkor faced a similar problem with food security and water delivery. Now it seems we too must accept the reality of restructuring our own systems for bringing food from the field to the table. Thank you.